And before I get started, I will emphasize a little bit about the importance of optimization in the deep learning. And optimization play a very important role in deep learning. Like when we map some problems arising from applications, right? And we can formulate this learning problem into an optimization problem. Like we optimize some training loss, and we may have some constraint, right? And then when we want to solve these problems, we need to use some optimization algorithms like stochastic redescent, right, to solve these problems. And today, I will mainly introduce some convex optimization, non-convex optimization, this basic knowledge, and also some optimization algorithms for solving these problems. And our main material today is based on the following three sections in the book. The first and second are from the book of high-dimensional data analysis with low-level models. And in Appendix B, that is convex set and functions. And in Appendix C, you can take a look at this sections about the optimization problems and the optimality conditions. And also our textbook Appendix A, there are lots of stuff on the basic concepts in optimization. Okay, we can get started. And today our lecture will mainly consist of three sections. In the first section, I will review gradient descent and proximal gradient descent, lots of stuff. And in the second section, we will take a look at what is stochastic and noise gradient descent. And in the final section, we will go from the optimization method to deep neural networks and also backpropagation. Okay. And actually, in the optimization, the most fundamental part is convex optimization. It's rather in this area actually has been well studied in the past decades. And in convex optimization, a central concept is convex set and convex functions. And here we first take a look at the definition of what is convex set. Here that capital X, right, belongs to a subset of n-dimensional Euclidean space. We say this set is convex if there are 2 points in this set, right, belongs to S, and an arbitrary constant alpha belongs to 0 and 1, such that the segment between these 2 points still belongs to this set. Then we say this set is convex. Like this one, we have the set, right? Like this set, and we pick up 2 points belongs to this set X and Y, right? And we draw a segment between this set, right? And like some point here, right? And this set, and this is a convex combination. And this XY because this is S, and this XY belongs to S. And the segment between these 2 points still belongs to this set. Then we say this set is convex. And here I give some concrete examples of convex set. You can see here. The first typical one is hyperplane, right? The AX, and that is X satisfied constraint. A transpose X equals B, right? Is hyperplane. In the 2-dimensional case, right, is usually a line. And the second example is hard space. That is the part below the line, and also on the line, right? And you can use this basic definition here to verify. Like all this set is here are convex set, and also find one example is the convex cone, right? And that is given 2 arbitrary points and draw a line from the origin to this point, right? And the part between these 2 lines are convex cone. You can use the definition, the basic definition, to verify all of this set are convex. And of course, we also list some examples of non-convex set, like the first 2 one. If you draw a line, draw 2 points right from this set, like this is X and this is Y, then some point like here on the segment, right, doesn't belong to this set, and then this is non-convex set. And typically, like this one, right? If you draw a point from like pick up point here and here, then you draw a segment, and then this point like lies on this part, right? Doesn't belong to this set, and it is non-convex. Okay, and then based on the concept of convex set, we can further define the convex functions. In general, we say that a function is convex if its domain is convex set, and also this f satisfies the following qualities. That is, you can see here, that is a convex, right? The convex combination for any point. Usually we call this one alpha x plus 1 minus alpha times y to be a convex combination of x and y, right? And at this point, the function value is smaller than alpha times fx, right, plus 1 minus alpha times fy. For all the x and y belongs to the domain of this function, and alpha is also from 0 to 1. You can see here, this is a very concrete example. What is convex function? Suppose like we have function like this, right? You pick up point, right, x here, and the function value at this point is fx, and then pick up point here y, and the function value here is fy. And then according to the definition, to draw a segment between these 2 points, segment like here, point, right? This point is y, this point is x, right? This point is y, and the function value is fx and fy. And what is this point? That is alpha x plus 1 minus alpha y, right? And at this point, the function value is this one. And then you can see here, that is the function value, right? The function value at this point is, the function value is here, right? This is this function value is smaller than the combination of alpha x here, this value, right? Point, the function value at this point is this one, is smaller than the alpha fx plus 1 minus alpha and y. And then we say this is a convex function. It's very basic. And here we'll also give some concrete examples like convex functions, like affine functions is a linear function plus bias tan, bias tan, and also like the norms. The definition there is like p norm, that is the summation of xi to p's power, right, over the 1 minus p, this power. And for any p larger than 1, and also like the both sum exponential, this different example, you can use the basic definition, that one, to verify all of these functions are convex functions. Okay, and then based on the convex function and convex set, this definition, we can further introduce what is the convex optimization problems. In general, it can be written down as the following forms. That is, we minimize some convex objective and also impose some convex constraint. You can see here, f0x, f1x, and until fmx, all functions here are convex. And then we say x is feasible if this point x belongs to the domain of f0 and also it satisfies all these constraints. And we say x star is global minima of this convex problem if fx star, the function value at this point, is smaller than for all other feasible points, right? The global optimum. And for the local minima, it's also a very straightforward. That is, we restrict to some point around x star, right? Around this x star, the function value is smallest in this neighborhood. And usually, for this theory, for very typical result is convex analysis, that is, any local minima, any local optima of a convex problem is global optimum. This is the classical result. I think you guys may know this. And also, for any unconstrained smooth convex optimization problems, if we minimize, that is actually the optimality conditions for unconstrained smooth convex problem. That is, we minimize some objective fx, right, without any constraints. And the f here is a continuous differential function that we say x star this point is global minima if and only if note that this is such necessary and sufficient condition that is at this point grading zero for convex optimization problems. Maybe I can draw some figure. Okay. And usually, like for convex, like unconstrained optimization problem, right? That is one typically. And for the global minima means at this point, the function value is smallest among all the physical points. The function values is smallest. That is global minima. And what is the like the? Of course, this is convex optimization problem. And then for this one, for this convex function, for any local optima, actually a global optima is also a local, right? Right? A global minima is also a local minima. A very good property for convex optimization, that is local minima is also a global minima. Like if we consider a common example that is non-class function, like this one. Okay, maybe like this. Typically, this one is non-class function, right? This function is like a non-class function on the 2D space. Okay. Okay. So you can see here. This draw more. Okay, like this. So you can see here, this like x1 this point, right? This function value fx1, right? And this is x2, okay. x2 fx2, right? Obviously, both of these 2 points are local minima, right? But this one is not a global optimum. Because what? Because this function is not convex, it's non-convex. So note that only here, this theory that is only and local optimum of convex function is global optimum. And this theory actually this result tells us for continuous smooth like this one, for continuous smooth function, right? Like very simple example, consider fx equals to x squared. X is a scalar, okay, and we take derivative like the two x equals to 0, right? Then x equals to 0. Then we can say this point is the global minima of this convex function, right? Fx equals to x squared. This very simple example of a convex function, and you can use this result to derive the global optimality, global optimal point for this convex function. Okay, any questions for the convex optimization problem? This is very basic. And you can know we go ahead. And here we give some concrete examples. I think Professor Ma have mentioned this example in previous lectures. That is convex optimization for structured data recovery. You consider that the setup is as follows. We consider a sparse vector recovery. That is to recover a sparse x0, right, from y equals to ax0. Y equals to a0. That is, we only have observed this y, right? Then and also this a is known. Then our goal is to recover this x0 from the observed samples. And in another setting, that is, we have some noise, right? The observed y is the noise version, not the clean version. And if for the first case y equals to a x0, then we can use this formulation basis pursuit to compute to recover the ground truth x0, right? That is minimize the optimization variable is x, and the objective function is the L1 norm of x, right? And the constraints ax equals to y. Obviously, the objective function here is convex, and also the constraint is a linear constraint, still convex. So the total problem is a convex problem, right? And the second example is also very classical, with a very classic problem. That is the Basel problem in statistics. The full name is least absolute shrinkage and the selection operator from this thing about 30 years ago. And the objective function is to minimize the square norm of y, the LT norm square, y of y minus ax, and the optimization variable is still x, and plus the L1 norm regulator here, right? It's obvious this problem is also convex in terms of x. Okay, and then let's go further. Then we will talk about non-convex optimization. Since like when we do academic research, especially nowadays, right, in deep learning and artificial intelligence, in CV, computer vision, in NLP, right, most of the problems we met are not convex, since it has neural networks. And the neural networks is what? Is combination of sigmoid function, the activation function, and the linear transformation. It's highly nonlinear and non-convex. Then in this case, this problem usually, like the problem we met in applications, is highly non-convex, and its optimization landscape will be very complicated, like this one. It has lots of local minimizers that are not global minima, and usually we say this kind of minimizers, local minimizers, the name is spurious local minimizer. And even in some case, the problem like have a lot of saddle point, right? Has a lot of saddle point. And if we run like gradient first order method, like gradient descent, stochastic gradient descent, we may get stuck in like this local minimizer, spurious local minimizer, or even at some saddle point. Okay. In general, we can write down the form of non-convex optimization as follows. That is, we minimize some objective function, and this f here, fx, may not be convex function, and also may have some constraint, and this constraint set c may not be convex set. And then the problem is a non-convex problem. It has been shown in the literature. This one, in the literature, in the worst case, note that in worst case, finding a local minimizer of a non-convex problem like above can be NP hard in the worst case. Not alone, let alone the global minimizer. Find the local minimizer is NP hard. Okay, like here we consider some typical examples. The first one is minimizing a quadratic function with binary constraint. You can see here the objective function is a quadratic function plus a linear function, right? And here for the quadratic function, the matrix Q could be indefinite. So the objective function may not be convex, right? If you take the second order derivative to justify the smooth convex function, the Hessian's Q is indefinite, then this function may not be convex. Okay. And also the constraint is also not convex, right? Not convex set is binary constraint. So this problem is a very typical non-convex optimization problem. And the second example here we consider is training a neural network. Like we use as data to denote the neural network. And of course, we do not write out the explicit form. Actually, in the literature, this one, it has been shown training like a just three node neural network is NP complete. Not let alone that like the neural network consists of many layers, right? And like the transformer, like other more advanced architectures neural network, training this problem, training those functions over this neural networks is highly difficult and is NP hard in first case. Okay, any questions? Well, and in practice, although the problem like we met in application is very complicated and it's non-complex, right? But we still try to work with, we still try to find some good points for this non-complex problems. And we want to explore the benign structures of the optimization problem. Some typical good, a relative benign property like the Lipschitz, the problem is smooth and has Lipschitz gradient or Lipschitz continuous hashing. And like for in general, we want to run some algorithm and then try to find a point that is a critical point. The definition is very simple. That is, at some point x star, we say a point x star is a critical point if the gradient at this point is 0. And the second one is we say x star, a critical point, right? This point x star is critical point. And we say a critical point x star is second order stationary point if at this point the hashing is positive semi-definite. I think you guys know what is positive semi-definite, right? No? Okay. We say a matrix. Say, let's consider a symmetric matrix like A, okay? We consider a symmetric matrix, okay? This denotes n times n symmetric matrix. And we say this matrix A is positive semi-definite, like use this notion, positive definite, positive semi-definite. If X transpose, okay, the AX is non-negative for any. This is definition of positive semi-definite. Positive semi-definite. Okay, positive semi-definite. First line, the abbreviation. That is definition of positive definite. A very concrete example. The identity matrix, right? 2 times 2. This dimension, identity matrix, you can use definition, right? Very easily to verify. This is a positive semi-definite matrix, right? Okay. Okay, and here we consider like a very concrete example as follows. We consider this function f(w). W is vector, has two components, w1 and w2. Okay, and then first we compute the gradient. This partial derivative is with w1, right? Partial derivative is w2. That is the gradient. And take the gradient to be 0. Take the gradient to be 0. Then we can compute the critical point. And then we verify, use this condition to verify whether this point is a second order necessary point, a second order stationary point. You can see here, we consider a very concrete point like 0, 0, w1 equal to 0, 0, w2 equal to 0. Obviously, right, it's a critical point. And the second order condition, you can get the hash is what? Hash matrix is all 0 matrix, right? Of course, it's positive semi-definite, right? It's positive semi-definite. So this point is what? Is a second order necessary point. Second order necessary point. But if you consider like epsilon, this point is what? Substitute this point into the definition, into the gradient. Gradient is what? Is 0, right? Oh, sorry, gradient is not there. Gradient is not there. The first component there, the second is not. But at this point, I want to say at this, like this one is critical point 0, 0, right? But you pick up some point epsilon around this point, around or 0 this point. The function value at this epsilon this point is smaller than what? Smaller than this critical point, the second order stationary point at 0, right? This shows what? This demonstrates what? Second order stationary point may not be a local minimum either, right? because you have find a point epsilon could be very, very small, could be very close to 0, and the function value at this point is smaller than the value at 0, right? Okay. And then here we also draw a figure, right? Very intuitive to take a look at the landscape of this function. Well, and then we can further introduce other different types of critical points. You can see the first and second we have defined in the previous slide, right? And the previous page. And the third here, the third kind of critical point is local minimizer or local maximizer. What is local minimizer? That is, at this point, of course, must be a critical point. And then the hashing at this point is positive definite, not just the semi-definite. Positive definite means the hashing of matrix A is positive. A is positive definite if X transpose A to X must be positive for any X that is not 0. Is positive definite. And is a local maximizer if it's negative definite. That is, X transpose AX must be negative for any X not to 0. Okay. And further, we can define what the saddle point. Saddle point means for critical point X star, its the maximum eigenvalue is positive, and minimum eigenvalue is negative. Okay, can you identify the difference? The difference among the definitions, the different definitions of critical points. Any questions? Like we also draw a figure to show the difference between difference among these different critical points. You can see here for non-critical point, right? That means at this point the gradient is not 0, and for minimizer, right, is positive definite local minimizer. That means at this point the shape, the optimization, the function, the loss landscape is like a ball. Is positive, is low minimizer and positive definite at this point. And what is saddle point? See here, what is saddle point? That means along some directions is increasing, and along some other directions is decreasing the function value. You can see here, right? It's like saddle the shape, right? Along this direction, the function value is increasing, but along this direction, function value is decreasing. Along this is increasing, along this direction is decreasing. That is saddle point. And also like maximizer is positive. Is negative definite, right? It's compact to the minimizer. Okay. Well, and note that for like a non-quantized function, it may have if its loss landscape is very complicated, it may contain all of these points, all of these critical points. It may have local minimizer, local maximizer, right? And also have like saddle points and also global minimizer. So that is why when we solve, like we will optimize a non-quantized function, it's very hard to find a like global minimizer because it has too many different types of critical points, and gradient descent, this first order algorithms, we can only guarantee it converts to the critical point. Okay, any questions? If not, we go ahead. Well, and then next question is how we can optimize optimization problem, right? How we can solve optimization problem. Although, like we said, we can use first automatic condition to identify what is critical point, right? For smooth function, we can use this point to define what is critical point. But how to find this critical point? Usually it doesn't have closed form, right? Like since problem we met in practice, the optimization variable x maybe a vector, or even sometimes is a matrix, right? You cannot directly to compute a closed form solution. So we need to use some iteration method to find the critical point. First typical algorithm we want to introduce gradient descent. Well, gradient descent is generally attributed to Cauchy. He's a great mathematician, right? He first introduced these algorithms about 200 years ago. 200 years ago. And in this short note, in 1847, Cauchy, in his short note, general method for the resolution of system of simultaneous equations, in this short note, he for the first time invent the gradient descent and use it to solve a system of equations. And actually, this what he found is actually boils down to the move in the direction of negative gradient. And the gradient descent update is very simple. That is, and here the k is number of iterations. In the next, how to generate the next iterate, that is, at the current iterate, we move along what direction? The negative gradient direction. And here the gamma is step size. And the optimization, we usually say the name the gamma is step size. But in like machine learning, deep learning, we usually call the learning rate, right? Different name, but same meaning. And a rule of thumb is take the step size to be 1/L. And this L is what? L is usually the Lipschitz constant of the gradient. And we will explain later in the next, next few pages, why we will take the step size to be 1/L. And here we plot some figures. You can see here, plot some figures. Like if gamma is very large, step size is very large, and the middle point here is global minimizer of this problem. And this different points is the iterates of the gradient descent. You can find, right, if this gamma is very large, the iterates will oscillate around this global minimizer. And you can see here, if gamma is very, very small, then we will move very, very slow to the global minimizer. And like gamma is to be probably chosen, we can move very quickly to the global minima using gradient descent. Okay. Well, and here we consider a very concrete function class. That is the gradient of a function, a smooth function f, has Lipschitz continuous gradient. And the definition that is for any x and y, the difference between the gradient at these 2 points can be bounded by L, a constant L, times the difference between x and y in terms of L to norm. That is definition of Lipschitz continuous of gradient. This definition, okay. And suppose we can always compute the gradient at all the points for function f, then actually we can write down. You can verify it later. You can verify it. Use optimality conditions for the. What is this problem? This actually is smooth convex problem, right? You can use the optimality condition for a smooth unconstrained optimization problem, convex problem. Verify. If you optimize this, you can derive the optimal solution is this one: x(k - 1 - L 1/L times gradient at this point. Maybe I can write down. Recall what we have learned for the convex optimization, right? That is, for convex optimization problems, right? The optimality conditions can provide for smooth unconstrained convex optimization. X is optimal, global optimal if and only if the gradient at this point is 0. So if you take the gradient for this problem, for this optimization problem, you can get what? For this take gradient with respect to X, right? Then we can first get the gradient of what? Of L times X minus, right? Then you can get the next degree X case to this one. Okay. Okay. And further, we have some interesting convergence ways of gradient descent for non-class functions. Note that here we don't assume this smooth function as to be convex. It could be non-convex. We don't require it to be convex, right? And here we consider a very general case that is minimize some general smooth function. Of course, it's non-constrained, unconstrained. Minimize a general smooth function, possibly non-convex. And actually, it has been well studied. The convergence rate of gradient descent for optimize a non-convex smooth non-convex function. The convergence rate very rather well studied. That is, the gradient descent with step size gamma to be 1 over L. The step size to be 1 is 1 over L. Then it converges to a critical point S star. And the convergence rate that follow, that is the gradient norm, the minimum gradient norm at some point, and xi is the difference, the iterates of the gradient descent. The smallest the gradient norm is smaller than alpha t, epsilon t, and the number of iterations k is at this order is 1 over epsilon t squared. That means what? That means if we want to find some point, right? Some gradient point, the gradient is close to 0. The gradient norm is smaller than epsilon t, like 0.1, right? Epsilon t. Then how many iterations will be? About 10,000, right? The number is it the number of iterations. The convergence, right? If this epsilon t to be 0.01, then the number of iterations of gradient descent is at whatever. It's about 10,000. That is the convergence rate for smooth non-class problem. Well, and we also give some concrete proof for this gradient descent. How to derive this convergence rate for gradient descent optimizing a non-class function, non-class smooth function? Actually, very simple. It's very simple. You can take a look at it. First, I will show this later. First, suppose that we have the gradient L wishes. Using the L wishes, we can derive the quadratic upper bound for this function. Quadratic upper bound, right? This is the linear term, right? And that is a quadratic term. And view refers to the quadratic upper bound. And use this quadratic bound, substitutes the gradient update, right? The gradient update into that quadratic upper bound. You can get this one, get the equality here. That is, the function value at xk at k rate is smaller than the last rate, k minus 1 rate, minus a term, that this term is 1 over 2L times gradient norm at the last iterate. It shows what? It shows the gradient descent with this step size 1 over L is always monotone decreasing, right? Function value is monotone decreasing. Okay? The function value at this iterate minus the last iterate is smaller than minus 1 over 3L times a norm square, right? And then that is this period. So then Then we summation over all the integrals of this. We get a telescope sum. Is it? We get a telescope sum. Then we can further get this, right? F(x0) minus Fxk is larger than 1/2L times the summation of the gradient norm square along all the iterate from I equals 0 to I equals k minus 1, right? Then we further can divide the minimum one is smaller than that, 2L over k. And of course, here we assume that the function f(x) has lower bound, f(x) is smaller, is larger than f(inf) for any f, this lower bound. Then we can get the minima of the gradient norm, right? And some integrate. It must be smaller than this. Then this Fx0 minus Fin is like constant. So we get a rate, right? And the L is also constant, right? The rate is like this, or 1/1 k, the norm square. Okay, any questions for this proof? Very straightforward. Well, but I left a key answer, right? Why we can derive the correct bound from the L-Lipschitz gradient. I can show you a little bit how we can prove this. Well, I think my teaching style may be a little different from Professor Ma. Usually I will write down some technical details. If you have any questions, just visit the technical details, okay? Right? L-Lipschitz, the gradient according to definition is what? It's gradient Fx minus, right? In terms of L2 norm, right? This is the definition for the L-Lipschitz. Then we want to use this to prove what? To prove this one, right? One. Then how to prove it? Actually, a very, very key step is to construct the function gt, and gt equals to this definition. Define gt to be f t is scalar, and x, y vectors, right? And we construct the function, construct this function. Then the fields, the remaining steps are very simple based on this one. You can see here, fy minus equals to what? Equals to G1, right? You plot T to be 1 here. You can have X, right? You plot T to be here. You get Fx, you get Fy. You plot 0 to be here, you get Fx, right? Then what happens? From a vector-based function, right? The input is vector, we transfer from there to what? To a scalar input function, right? So let's go on. Okay, now use the fundamental calculus theorem. We get this equals to what? Is it the fundamental calculus theory, right? Actually, you guys should know this. Yeah. So then compute this. Compute the gradient. The derivative, actually, this is not gradient, it's derivative of gt, right? The derivative of g prime, the derivative of gt is you can write down it. Actually, red to snow. Yeah, you can verify the derivative of GT is actually this one. Inner product of gradient of f at this point with y minus x, and further. And we introduce this term, the inner product with y minus x, right? Is this is derivative is not is dt, right? Dt, not dx. Is scale. And plus what? Plus gradient, right? Sorry, the inner product y minus x. Since in this term there is no equation for t, then we can further show that what get fy minus fx. Remove this term to this side. Reorganize it. And use the quantity here, right? The xy. Use this quantity. X transpose y, the what's smaller than the algebra, right? And so we get use the equality here to here. That is, we get times y minus x, right? And the equation can be is here since the sorry, the equation is 16. Okay. And then we can use the Lipschitz. Can you see? You guys can see. And use Lipschitz continuous here, right? This is we can use Lipschitz continuous gradient here, right? Lipschitz continuous, use this one. Then we get t minus x. Okay. Right. Then we get one is smaller than. Right? Then this equals to. Oh, there's L, right? L Lipschitz. Is L Lipschitz. So we finally get smaller than. That is hopeful for the quadratic outbound. The key step in this one is define this scalar-based function tt, and then use fundamental calculus, and then use the quadratic outbound, the Lipschitz gradient, that equality, and finally you will get the quadratic outbound. Okay. Well, let's go further. That is, in the we just consider a very simple case, right? Smooth function, smooth and possibly non-convex. But if we have some non-smooth term, how to handle it? Actually, also well studied in the literature. That is, like here we consider fx to be a sum of a smooth, possibly non-convex function with a non-smooth convex function. This one could be non-convex f, but it's smooth, and that Tx is non-smooth, but it could be, but it's not, but it's convex. Then similarly, we can first, and we assume that f is Lipschitz continuous, really Lipschitz continuous. We can first construct a quadratic outbound for this fx at some iterated xk, k denotes the case iterate, construct quadratic outbound for there, and add that non-smooth term. And then we rewrite this form, right? It's actually can be rewriting this form, the quadratic outbound. Then we go to minimize the quadratic outbound. Then finally we'll get it iterated like this. That is arguing Tx. the non-smooth term plus the quadratic function, right? It's approximate term actually in the literature. This one is approximate term. And this function is actually what? Is a strongly convex function. Since G is convex, G here is convex. You guys know what is strongly convex? Strongly convex. Like for smooth convex function, right, the gradient is usually the Hessian is positive semi-definite. And strongly convex, that means the Hessian must be definite. That's strongly convex. Yeah. Right, and this problem is strongly convex, so it only has just one unique global minimizer. But the problem is this problem also in practice, right, is a convex plus a quadratic term. But G, the main difficulty here is G is non-smooth. So how to solve this problem? Even if it is not convex. Unfortunately, before I talk about how to solve this problem, we need to introduce the subgradient for non-smooth function. Subgradient for non-smooth function, you can see here. G is a subgradient for convex function f, and x belongs to the domain of f. If and any y and any y there, for any y there is a quadratic, there is a linear, there is a hyperplane at x, right? And here this fx plus g transpose y minus x is like the linear hyperplane, the hyperplane for this at point x. And then we say this is just a definition. Then we say this G is a subgradient, and the set of vectors is a subdifferential of f at this point. We denote it as partial, like that notion. That notion denotes the subgradient. This is draw a figure to demonstrate what is the subgradient for convex function. Like we consider a very concrete example. You can see here. Fx is just a scalar function, right? This is non-smooth, right? At this point, fx equals to x at absolute value. This is non-smooth function at 0, right? So, what is the definition of the subgradient? That means you find a hyperplane at this point, right? For all y up, that is above this hyperplane. That is the definition of subgradient. So you can see here, there's concrete example, like we consider the pointwise maximum of two convex functions. F1 is convex differential function and F2 is convex differential function. There's a concrete example. That is, you have this is F1x, like this one. And this is F2. And then we take the pointwise maximum. Then what is left? The left part is right. This is the left part. Right? This is, and at this point is non-smooth. This is F1. F1. This is F2x. Right? The maximum. This is the maximum. F1x, F2x. Right? Then you can see here. We can compute the gradient, the subgradient of this function. If and this is if we don't consider this point x, if you know x 0, if we don't consider this point and all other points smooth, so the subgradient reduced to what? Reduced to gradient. At all smooth point, the subgradient reduced to gradient. But at this non-smooth point, the subgradient is a set that is a convex combination of the gradient, right, of F1 and the gradient at this point of F2, right? The convex combination. And alpha is from 0 to 1 is convex combination. That is, you can see here. What is interpretation of this? Actually, that is the supporting hyperplane. Yeah, that is subgradient. Okay. And based on subgradient, we can get a very very important optimality result, optimality condition for non-smooth optimization problem. You can see here. Suppose f is a convex function, but it's defined on the extended value domain that is union of R and positive infinite. Positive because maybe this R is not smooth, have some constraint, so we use the positive infinite this to handle the indicator function. Then we say x star minimize is global minimum of f, right? If and only if the zero belongs to its subgradient. Note that this is necessary sufficient condition. The proof is very, very simple, just one line. You can see here, use the subgradient, this inequality. And at this point, right? At this point, x star, we have 0. So that means what? That means you can show along this direction, you can show for any y, right? You can show fx, fy is larger than fx up for any y. And along another direction, you can also get that. From this, you can first from this direction to this direction, and also from this direction to that direction. So then we can show this theory. And here, we consider like example, very simple example, fx. Oh, sorry, here should be absolute value x. It's not the x. The example I want absolute value of x, right? At this point, at x star equals 0 at this point, the subgradient is -1, 1, right? Subgradient computed verify use definition. The subgradient is -1. This interval, and then 0 belongs to -1 to 1. So 0 is global optimal of this function. Okay. Any questions? So optimality condition for the non-class problem. Sorry, for the convex non-smooth problem. Okay, so based on the above, we have further introduced the prox operator. Since in the previous lecture, right, we talked about if we apply like this proximal gradient, this averages to solve this problem, a smooth non-class function plus a non-smooth convex function, we can like construct radical around and then finally get the iterator like this. We have the sum problem gx plus this and plus proximal term. Then we can further define the proximal gradient of a convex function as follows. Note that actually this is just a notion. That is this is notion. This notion means when we write down this notion means we want to compute the global minima of this convex problem. The global minima of this convex problem, right? And if we use this notion, we can rewrite the proximal gradient descend, the iterates. We can rewrite this iterates to be this form. Be this one, be this one, be 6. Just so we just use notion to rewrite the updates. So fortunately, for many convex function, for many this convex function, even it's non-smooth, this proximal matrix, this proximal operation has closed form and computed efficiently. Here we give two concrete examples of proximal regions. My first one is very typical. That is this T is L1 norm. You can see here. If we plug in the L1 norm into that function, that optimization problem, you can actually show that the prox mapping for this function is essentially a soft speciality function. It's element-wise soft speciality function, like you see. The ith component of this soft speciality of this proximity operator is this one, the source over this function, and this function is defined to be the sign. Take the sign of wi times maximum between these two elements. Well, you can concretely write down what does this operator mean. The proximal operator. Actually, it means this proximal G W, the ith entry is equals Wi minus lambda if Wi larger than lambda. You can verify if Wi is positive, then psi is what? Psi is 1, right? And absolute value, wi is wi, right? Minus I, minus lambda. Use it is larger than lambda, so you can get this, right? And for the second one, for the second case, if wi belongs to minus lambda in lambda, what is value is 0, right? And then for the last case, it's wi plus lambda. So why the name is so much speciality? You can see this, right? Because wi, this the variable, the value is belongs to minus lambda and lambda. We will take it to be 0, right? That is what is mean here. Okay, and we draw a figure here. This is so special. You can see belong between this region, right? In this region, in this interval minus 2 and 4 and lambda, minus lambda and lambda. Okay, we will take the value to be 0. And another typical case for the proximity we consider is TX, is to be matrix nuclear norm. Right? This actually is a very typical the non-smooth convex function. And then you can also use the definition of proximity, proximal region. You can show that is the proximal region table of this form. Is a singular value solved speciality. That is U times solved speciality, those two matrices. And this sigma is the diagonal matrix element by solved speciality. And here the V, and the V is the U sigma V SVD of W. That is, you first apply the singular value decomposition to W, to this W, and the next apply the solved speciality to the sigma, and then you will get the proximity there. And this solved speciality is and component-wise applied to the single values of W, that is diagonal elements of W of sigma, right? Okay, and here we use a concrete example to demonstrate how to compute the approximate region of the L1 mole. Compute this one. You minimize this convex problem. That is, this is not smooth convex function, right? Plus radical function, approximate. Then how to compute the closed form of X? Actually, very simple. Just to use what we have introduced before. The automatic condition for subgradient, automatic condition for non-smooth convex function, right, is 0 belongs to the subgradient. This is gradient is X minus W, and the subgradient of this can be written down like this form, right? Yeah.
On the whiteboard, for the your solution if W1 and Wi is smaller than negative lambda, it should be negative Wi plus lambda.
You mean this one? Is negative.
Yeah.
Yeah, you can see this figure.
Yeah.
You're right. Yeah, you can see so that figure, right? You can see that figure. And here, what I want to show you guys is how to compute this closed form for this proximity. Just use the automatic condition for non-smooth convex function. Why we can write down like this form? Because this function, you know that is component-wise severable. Component-wise severable. You can decompose into, for each entry, this problematic condition, right? Then you can apply to each component, and then you can show from this, you can derive this one. So here we can write down the whole proximal gradient algorithm as follows. The function class we consider is a composite function. That is the summation of a smooth, possibly non-convex function with a convex non-smooth function. And here we also assume this gradient is L-licious and G is convex non-smooth, right? And the basic iterations, that is first we take a gradient step actually for the f, right? Pick gradient step, and then apply the proximal region to this WK. That is the whole update of the proximal gradient descent. And it has been shown in the literature that is, if this f is convex, we can show very, very good rate that is convergence with 1 over k. It's very fast, like you run 2 iterations. You can get a solution that is like accuracy 0.1, right? And but if it's non-convex, the rate well, that is 1 over square root k. The k is number of iterations, right? Number of iterations. Okay, that is convergence. That is the proximal gradient algorithms. Well, highlight speaking, right? But high level speaking, what is the main intuition of proximal gradient descent? That is, we first consider a quadratic upper bound, right? For this convex, for this smooth part, right? You can see here. Construct the quadratic upper bound and use the Lipschitz quality for this smooth part, and then keep this non-smooth part, non-smooth convex part. And right, then you can write down the whole iterations like this. Then this is subproblem, and this subproblem reduce a very classical, a very easy to compute subproblem, right? Like we said, for some T or V spatial structure, this subproblem needs a closed form solution. Here we give a concrete example. Like for the problem we have introduced before for the last problem. Right? This is typical the composite of a convex smooth function plus convex smooth problem plus the non-smooth convex function, right? And a very straightforward way to solve this problem is use sum gradient, right? Use sum gradient and view this as one function, and then apply the sum gradient. And actually, you will find it converge very slow. This you can see the convergence formula. This x is number of iterations. The y is function value to the global optimum. You will find it converge very slow. But if you use the proximal gradient algorithms, this red line, right? Like the update like this one. And then we'll find it converges very fast. Actually, it can be shown in the literature. Proximal gradient for Lasso problem converges linearly. It's very fast. Subgradient convergence rate is 1 over square root of k. Very, very slow. Yeah, that is magic of proximal gradient method. And questions for the proximal gradient. This is very typical. And actually, there's a name in the literature for this proximal gradient for Lasso problem. That is iterative solved speciality algorithm, ISTA. Now, I think you guys should figure out why we have this name, right? Because arising from the prox mapping of L1 norm, right? It's the operator. You compute this prox operator is a solved speciality function. Then the whole name you get is iterative speciality algorithm. Okay. And then we will want to talk about some connections between this proximal gradient algorithms for Lasso problem and neural networks. I think Professor Mao may have introduced this concept, right, a little bit in the previous lectures. There's very natural connections between a neural network and some optimization algorithm. That is, if you unroll the iterations of proximal gradient for Lasso problem, then you will get a neural network. You unroll the iterations, you forward way, you can get a neural network. And concretely speaking, you can see this slide, there's network connections. Using unrolled optimization, you can get some neural network from the objective from the Lasso problem, right? For the ISTA that is proximal gradient descent applied to the lasso problem. Right? The probe actually is a fixed point of this equation, so this element that is the updates of proximal gradient for lasso problem. And that W is this one, and S is this, and you can plot the updates of one proximal equations, That is first apply W to Y's input, and then like have this as this pass to here, right? And then apply a solver speciality. And if you consider time unfolding version of this evidence, like in the fold approach, you unroll these iterations, then we'll get what? Get a new network. And you of course you need to truncate it to some fixed iteration, like you truncate it to three iterations, then you get a straight neural network, right? But here a very key concept that when we construct unrolled optimization to construct neural network, you need to learn the parameters of this neural network use back propagation. That is in the backward process, you need to learn the network parameters from the data. That is the W and S usually are learnable in applications. You need to learn it from the data. And this paper actually arises from very, very famous paper by Ian Locke and his student the Carol. That is this paper is published in 2010. Learning fast appropriation of fast coding, very, very fast paper. Also this approach is known as LISA, learn LISA. And interesting that is this way, the connections between the proximal gradient algorithms and the construction of neural network provide a very good approach to understand, we interpret the neural networks. Okay, now let's move further from gradient descent and also proximal gradient to other algorithms, to other first order algorithms, accelerated algorithms. The first one I want to introduce is heavy ball map. This is also very well-studied algorithm. It's first proposed by Polya in 1964. In this paper, 1964. And actually, you can see here the gradient descent, right, for unconstrained smooth optimization problem is very straightforward. Take gradient descent along the negative gradient directions. And heavy ball, this method, also sometimes in the literature we call it momentum method. That is, we will add a momentum term to the gradient update. You can see here, what is the momentum term? That is the difference between the current iteration and previous iteration, right? Like you want to generate the next iteration. You not only use information from the current iteration, you also use information from the previous iteration, right? This is the heavy ball method. And this method motivates the popular method in the deep learning. That is ADAM, right? ADAM, this algorithms share the similar spirit to this method. Well, it has been shown in the literature. In the worst case, this algorithm may have no acceleration for gradient descent, but in some well-defined, in some good case, this algorithm can achieve over K-12. This conversion route obviously is much faster than this worst case conversion rate, right? Yeah, that is a heavy ball method. Well, I think heavy ball method the idea is very natural. That is, when we want to generate the next iterate, we will not only use the information at the current iterate, but we also want to utilize the information from the previous iterate. That is the heavy ball method. And the next accelerated gradient descent algorithm is invented by Nestor, a very, very famous optimization expert. he has lots of highly cited paper in optimization. Yeah. Go ahead.
I can understand if we add the momentum term to make loss equation develop faster with the optimization faster, but how could we theoretically prove the convergence rates better?
Yeah, good. You mean, we theoretically show this kind of salary
Yeah.
in the gradient descent, right?
Right.
Yeah, there's. Yeah, I think I should sell later. I will show the paper that I can show this rate in the WeChat group. Yeah, actually there are some theoretical justification on the convergence rate, faster convergence rate of Haber-Bosch method. Yeah, good question. And then we want to introduce this accelerated gradient descent. Well, the idea is a little different, but still a little different, but still similar. You can see here. The idea is also like use the information from the previous iteration, not just current iteration, right? You first construct a auxiliary point pk plus 1. Use not just use iterate xk, but also previous iterate, right? And then you can see the difference from the Haber-Bosch method, right? Now you compute gradient as well at the auxiliary point, right? Not the gradient at xk, right? You can see here in the Haber-Bosch method, you compute the gradient at xk, right? But in the accelerated gradient descent, you compute the gradient at this auxiliary point, and also take the gradient also take step not at xk, but at pk plus 1, the auxiliary point, and then you need to carefully choose the step size alpha and also this extrapolation parameter. Usually in optimization community, they call this term like extrapolation of momentum term. This is the answer to control the momentum, the length of momentum term. Yeah, is this beta? Okay, and you need to carefully choose it. And theoretically, they can show that you can choose this 7 parameters. Well, actually, in this paper about 40 years ago, right? 40 years ago, he shows that use this step size, this accelerated gradient descent can achieve for convex problem can achieve this convergence rate 1 over k squared. Yeah, in this paper. And yeah, go ahead.
Sorry, what's K?
K is number of iterations. Oh, it's here. Yeah, it's number of iterations. Yeah, number of iterations. And note that you can see here, for this accelerated gradient descent and also for Haber-Bosch method, usually you cannot show the function value is monotone decreasing. In gradient descent, right? What we have shown in the when the function is Lipschitz, when we prove the convergence rate, what is the first property we show? You can see here when we derive the convergence for the gradient descent. First, we show what the function value is monotone decreasing. But for this accelerated algorithms like the Haber-Bosch method or accelerated gradient descent, you cannot show the algorithm is monotone decreasing. Sometimes the function value could increase. So, but even in this case, Maxwell have some very clever idea to prove the convergence rate for this accelerated gradient descent. If you are interested, you can take a closer look at the technical details. Well, and also second thing I need to emphasize that is 1 over k squared. That is optimal convergence rate for first order method for solving complex problem. You can never show better rate than this rate. 1 over k squared is best rate you can achieve. Optimal rate for a more first order method for complex optimization problems. Okay.
Sorry.
Yes.
But you said like it was the number of iterations.
Yes.
But this doesn't all depend on the. So this is time complexity or.
Yes, you mean is there any dependence on other constants or something?
No, I mean like because if the O is the time complexity, the K is the number of iterations, then how is it that
Hmm.
the time complexity is like a fraction of the number of iterations?
Actually, it's like this, I think. I have xk minus fx sum function value. Yeah, like this. Yeah, this is for the convex problem. So you only have one global optimal, right? If you use global, right? The global optimal value. Yeah, so you can show that. Okay, okay. Good. Okay. Yeah, actually, we right now the conversion rate is intense. Is converted this way. The function value gap is converted at this rate. Yeah. Yes, here. This is the whole details of accelerated gradient descent. In Nestor's paper, there is accelerated gradient descent. The function class we consider is convoluted function, right? It's convex smooth function plus a non-convex, plus convex possibly non-smooth function. And the basic integrate for the is like construct some point right P of the delivery point, and then iterate it with P in this percent. And you carefully choose this set of parameters and update it like this one. This proximal gradient descent uses the accelerated proximal gradient descent. And it has been shown in the literature this algorithm can achieve this way. The function value gap convergence at a rate of 1 over k squared. Okay. And then in the previous pages, we talked about how to use proximal gradient descent for solving lasso problem, right? And then actually, and we can also apply this or accelerated proximal gradient algorithm for lasso problem. The problem is still like this one. And then if we use, then we apply proximal gradient, then the update is like this. We construct some actually the auxiliary point and then compute the gradient at this point, and then apply the proximal operator. And is it, this algorithm is the name that is FISTA, fast iterative specialty algorithm. Yeah, it's FISTA, it's very famous. I think it's really famous about 20 years ago. Yeah, in convex organization in this community. Okay, and when we talk about this, I want to say something interesting. That is, since I get my when I in my PhD period is about 10 years ago, I think is 2016. At that time, few people studying like deep learning and this stuff. And at that time, of course, there are some people are studying like computer vision and natural language processing, but most of what we use is not like the deep learning, is not based on deep neural network. What we use is like this optimization method is very like based on the quadratic automatic constructor, and then it run the gradient descent the algorithms. And the model we use is like linear model, quadratic model, like a PCA and this algorithm. At that time, we don't use like the neural network. But I think after like about 2016, from that time, after the release of ResNet, and the deep learning is getting more and more popular. And from that time, and from that period, I think like optimization, especially convex optimization, few people are interested in it. Yeah, most of the people are goes from the optimization community to the deep learning and also CV pieces communities, and especially now the spatial foundations of optimization. Yeah, is now it's very small group compared to the deep learning. Yeah. Okay. Let's go ahead. In the previous lectures, in the previous pages, right, we mainly talk about the deterministic optimization, just run some gradient descent, proximal gradient descent, or some accelerated algorithm for solving this problem. And now we will turn to the stochastic gradient descent. Stochastic gradient descent. I think this is really widely used in deep learning, right? Most of the guys like when you run some algorithms, it's that, or like stochastic descent, some adapt algorithm, this algorithms. And recently, a very popular algorithm that is more for solving the larger longer model problems, right? Moon. And here we will take some close look at what is the insights of stochastic organization. In general, you can write down the stochastic organization of objective function like this, right? You minimize some those function L, Lx, and here you can actually it's like this, it's like take expectation with respect to the random vector W. And this loss function LW is divided on this random vectors. And more concretely, you can write down use integral, you can write down like this one, is the integral over this probability distribution and integration for LWX. And here, W is random vector and the distribution, whose distribution is P and supported on some absolute this subset. Okay. And when we use stochastic gradient descent, the basic update that follows, then at iteration K, we sample some random vectors. I think this may be different from what you guys see. You already define the sum, right? The form is final sum. And this is generalization of that form. And I think in most of paper, with math, it's like consider like I equals to M, like final sum, like some. X I Y I sample from some distribution. Like this form. But here we consider a very general form, the expectation. Since if this WK or this W is like the empirical distribution over samples, you will get the final sum form. Right? Okay, and then you perform the basic updates of the stochastic gradient descent, then you randomly sample some WK from the distribution, and then define this LK for the loss over this sample WK, and then perform a gradient step over this WK, right? Compute gradient and this sample vectors, sample random vectors, and then here the eta is the learning rate. That is based update of the stochastic gradient descent, very simple. It shows the same spirit of the gradient descent. Note that in stochastic gradient descent, when this this is omega k is sampled, is a specific and fixed sample once you sample. But why we like say stochastic gradient descent? Because this omega k is random across different iterations. Okay, here we consider a very, very interesting example. That is very simple. But in this example, we can show that stochastic gradient descent may diverge, may not converge for solving this optimization problem. You can see here we consider we have m possible value for omega 1 until omega consider 1 to consider n, and with probability 1 over n with equal probability. Then the loss function L omega take on this form 1 over 2 x minus omega non square. Then you can verify it. Right? That is, you can show this problem. The omega solution must take on this form. The average of all samples. That is optimal solution. But when you run the stochastic gradient descent for solving this problem, for solving this, you will find that you will observe this phenomenon. That is, this vanilla stochastic gradient descent always oscillate around the global solution. This you can see. These are some samples. This one is some samples, and this one is closed solutions. According to this one, according to this closed form, you will find the equations of gradient descent will oscillate around this point. May not converge. Just use vanilla stochastic gradient descent. Okay. However, if you add some like momentum term to the stochastic gradient descent update, you will observe this. You will converge very fast to global solution. So this simple example, why we show this simple example? Because we want to introduce a very, very popular evidence again, right, is actually also share the same spirit of the momentum method, right? You can see here, this is the whole update of that. Well, this this algorithm is first proposed by these two authors. And this paper is accepted about 10 years ago in IQ. As far as I know, this paper has been cited over 200,000 citations just over 10 years. It's really crazy, right? And the interesting thing for this paper is when these two authors in their paper, they derive some convergence rate for this algorithms. Convergence for this algorithm, but actually is wrong in their first release of this paper, and then later this gap is fixed. Yeah, it's just we have to admit this problem. This algorithm update is too complicated. You can see here the whole update of again this stochastic descent algorithms. That is first at the iteration k, we sample some sample some WK from this distribution and compute gradient. Okay, GK, and there are two very clever design. The first use the first momentum. Use the first moment. Actually, this is like a momentum of the gradient. You guys see construct right MK this auxiliary point based on this gradient. Okay. And second, you do what? Use the second momentum information. It's like scaling of the gradient. You can see this is element wise product of GK. Okay. And construct another auxiliary point BK. Basically, right? This not only use like momentum method, right? Usually have this step, but it has very clever design here. Take over the element wise product of the gradient, and then do some bias correction estimates that is like a normalize this MK and VK. And finally, update. The updated tool is also very complicated. It's like use this constructed M hat, okay, right? Element wise, the division over element wise division by the square root is also element wise square root of VK hat. So here and plus some epsilon. And here, this epsilon is usually to be very small, like 10 to minus 8 small, to avoid the division by 0. And this beta 1, here, beta 2 are some parameters to control the decay rates, to control this decay rate. And usually is from 0 to 1. These are decay rates. And this is the whole update of ADAM. Actually, the ADAM, I think it is really the clever, right? The idea use not only use the first moment information, but also the second moment information. And this update also like adaptive adapted the rule to update the learning rate of the algorithms. Yeah, like when I run some experiments for like some deep learning problems, usually stochastic gradient set may take 10,000 iterations, but not converge. But usually if you like run this then it converges like 200, 300 iterations. Yeah, it's very amazing. Okay, and the next one, after we introduce the stochastic descent, we will take a quick look at the noise gradient descent. Of course, this is different. I think the noise gradient descent, this here we consider a very concrete noise gradient descent that is logarithm momentum column. And the function we consider is a Lipschitz, is a function with Lipschitz continuous gradient, and the Lipschitz states L. And we can access the gradient that is first order. And here, this n is a small random noise. This n is smaller than random. The logarithm column, the noise gradient descent. Note that this noise gradient descent is different from stochastic gradient descent, right? Since you can see here the update. If you don't consider this part is 1, it is essentially gradient descent, right? But after this gradient descent, take this step, you will add a noise term from here. This NK is noise is usually this NK is sampled from the random Gaussian. the distribution, the Gaussian, the mean is zero, and the covariance is identity. And this lambda is to control the noise scaling. It's very straightforward, right? The noise gradient descent. And a very interesting result for this noise gradient descent is you can show that if gradient norm is large, okay, larger than 2L times epsilon and square root, you can show that in expectation conditional on the last iterate, it decrease as this decrease, right, at this value. That is the next iteration, the conditional value is smaller than fx the current value, current factor value, minus this epsilon plus lambda. Well, this you can find it as, or I should mention that you can find all proof like the conversion proof, convergence rate proof, in the Professor Zhongmai and Professor Ima's book, high dimensional, that book. In the appendix B and C, you can find all the proof. And like this one, you can find proof there, detailed proof there. Okay, and note that if you consider like this epsilon to be lambda, right? Like at some point, at like the gradient norm is larger than this, then you can get what? You can get the conditional, right? This epsilon equals to lambda, right? You can show the conditional expectation is smaller than FSK, right? Yeah, that shows what? Expectation, noise gradient descent is decreasing. Yeah, that is the noise gradient descent. And a very interesting phenomenon, very interesting result, I think, that is the effect of noise gradient descent around a set point. Like we will consider a quadratic function, very simple, right? F the quadratic function x transpose hx, and h is the n times the square matrix, and its minimum similar eigenvalue. Sorry, here we assume this minimum eigenvalue is negative, and the largest eigenvalue is positive. Okay, and here you can compute the Lipschitz constant should be at the maximum of the absolute value of the eigenvalue, right? That is Lipschitz constant. Then you consider the Langmuir dynamics becomes like this form, right? You can write down the Langmuir dynamics. There is this form. There is I minus h, right? Minus over L times k, and plus a noise term. Then we can show that actually this updates can escape from the set point. Can like if it stays from the set point, it will run away. This problem, what is set point of this problem? Actually, if x equal to 0, that is set point. You can see here why it can escape from this set point. We show some details. You can see this lambda x, right? We denote it as this as A, this as B. You can compute the maximum eigenvalue of A is positive, is larger than 1. Then you can show this actually is a very unstable linear system, because you can write down the whole update and the accumulated weight. You can show the tasted weight take of this form. And since we know the largest eigenvalue, the simple eigenvalue of A is larger than 1, then what happens? The system will blows up, right? Goes to infinity. This term. Okay. So this shows this system is not stable. Okay. And which action will survive in this in all the iterations? And also in the literature, they also call this with Power iterations to compute the leading eigenvalue of an algorithm, right? Power iterations. And it has been shown in the book. This noise gradient descent can escape from set point. That is, you consider noise gradient descent will the Monte Carlo distance rate for this function, starting from the Gaussian, random Gaussian, mean 0 and covariance sigma square identity. Then after this number of iterations, you can see what? You can see the function value over the starting point is conditional function value, right? The gap, k plus 1 is smaller than minus lambda, right? That says the function value significantly decrease over the initial point, right? In expectation. Okay. Well, and in the fine, I think I only have time to talk about the fine slide. This is one of my recent research. I think it's really interesting. That is, I can introduce some very advanced result for escaping from the set point. In the previous literature, in the previous slide, I introduced what is set point, right? That means the hashing along some direction is positive, along some other direction is negative. Here we consider the string set, that is, we consider a unconstrained smooth function, and we say one point is string set, that is, this point must satisfy the first order condition, is critical point, and then along some direction is negative, along the minima eigenvalue direction is negative. Okay, and so is global maximizer a string set? Is or not? It is, right? Global maximizer is since global maximizer satisfy the positive, the hashing is negative than that, so it must be a string set point, right? Look at this definition. It has been shown in this paper. It's just 5 years ago. Jason Lee, associate professor from the University of California, Berkeley, Berkeley. They have very great paper, I think, very impactful in the optimization community. They show that first order algorithms, not just the gradient itself, maybe other algorithms use gradient information, can escape with random initialization, almost always avoid strict set point. You know what I mean, right? That means if since your gradient set we say may convert to a critical point, right? But this result tell us a very important result. That is, when this critical point have some additional selection, it's a strict set, then gradient descent will escape from this point, from this kind of critical point. Okay, right? What is implications? Like you have optimization problem, your landscape like this has some global maximizer, local maximizer, and also the global minima strict set. If the problem only consists of these types of strict set points and also the global or local minimizer, then gradient descent with random initialization almost always converts to local global minimizer. Yeah, this is really important result. That demonstrates why, like, when we train some neural network, you can obtain some very good solutions. Because in many cases, you can show the training loss you consider have some good landscape. That is, critical point only consists of two kinds of solutions, two kinds of critical points. The first one is the strict setter. The second is global minimizer. So gradient descent can escape from the strict setter. So gradient descent can only convert to global solutions. Right? Yeah. So when you want to explain some phenomena in the training some neural networks or some problems, you observe, well, you convert so well, you can always find some good point. You can use this theory to explain it. You can show the training loss. Has full landscape. That is, the critical point only have two kinds of solutions: local or global solutions or strict set points. Okay, I think I should stop here. And the left slides, I think Professor Ma will talk about it in the next lecture. Thank you.